thank very much. Like Max invited me in this to give this talk, and thank Nakano-san, which is interested in my research in this area. So today I will talk about how could it be like more disorder. If you put more disorder in the system, it actually leads to bigger conductivity instead of make it smaller, as many of you might expect it. So this work is put in this archive paper already. If you are interested in details, you can take a look at it. So it's my great honor to give a talk in Topological University here. So before I dive into details, let me just do a crash course in physics about insulator-metal, because I realized that maybe many of you are not from physics side. So I want you to at least learn something, whatever your background is, from my talk. So for real material, for material in real life, many of them are made by lattice, which means atoms are distributed periodically in space with some lattice constant A. Here I show a very simple model, which is one-dimensional. This red crossing dot represent the nucleus positively charged, and there's electrons around it. So electrons are sitting inside the periodic potential made by those nucleus. For physicists, we are more interested in the momentum space or the K space. This is just the Fourier transform from the position space or the real space. So if you go from a periodic real space lattice to its Fourier image, you will get also a crystal, but of different period. So from Fourier transform, basic knowledge from Fourier transform, now the period becomes 2 pi over A. So in K space, you also get this periodic lattice. Because of the periodicity, we can only focus on one period of it. For physicists, we call the first period in the K space the Brillouin zone, where the period is centered at zero momentum. So here I will show you a very crash course. How do you define? How do you get a band from a band dispersion from this knowledge of periodicity? So I will take an example of photonic crystal. So the energy, this is epsilon. Epsilon represents energy, disperse as a function of momentum linearly. So if there's no periodicity in the system, they would go just like two lines, linear. However, when we keep in mind that the system has periodicity, whenever the line crosses the first Brillouin zone boundary, we should fold it inside the first period, the Brillouin zone. After we've done with the folding, the first period or the Brillouin zone will look like this. It's like part of the chessboard. There's some square structure inside of it. And there's a crossing point. There's some crossing points inside the band spectrum. In physics, those crossing points represents degeneracy. So, which means there are 2 points with the same energy in the spectrum. And in physics, by perturbation with help of the periodic potential, electrons will leave this degeneracy, and this end up with some bands. So for example, here I show you after the lifting of the energy degeneracy, you got some energy gap between the bands. This is the first band, second band, till the fifth band I showed here. There are more up above it. There are more bands above it. Here I only show you one-dimensional model. In real life, momentum is 2D if it's 2D material and 3D if it's three-dimensional material. So this one-dimensional curve becomes higher dimensional manifold. So indeed, it looks like just band in real life. So that's a crash course of how do we understand the band theory. So later in this talk, I will talk about a more specific example, which is the small gap semiconductor. In this model, the energy dispersion has exactly the same linear dispersion as I described it above. The only difference is that I include the gap in the dispersion. So after I add these gap terms, we can describe the magnitude of the gap as 2 delta. So here I show you 2 bands. In physics, we call the upper band the conduction band, the lower band the valence band. And for fermions like electrons, they obey Pauli exclusion principle. More easy way to understand it is just using an analog of water. You can think of electrons just like water, because Pauli exclusion principle basically say that no 2 electrons can occupy the same quantum state. So if you put many electrons inside a system, they have to occupy different energy state. So it's just like if you pour water in a cup, they have to they will fill the cup according to how many water you put inside of it. So for example, here I show you a case where the highest occupied energy, which we call the Fermi level, is put inside of the gap. Because this is the highest occupied energy. So all energy below it should be occupied. And this makes the valence band full. So all the states inside the valence band are occupied, and all the states inside the conduction band are empty. This case is actually what we call the band insulator. It's called band insulator because, maybe I should keep it in this slide. It's called band insulator because all the band states in the valence band are occupied. So there's no empty state for electrons to use in order to move. So electrons, for an electron to move, it has to get excited to the conduction band where there are many empty states for you to available for electrons to use to move in space. Because for an electron to move, it has to go outside from an occupied state to an empty state and keep going like this. Otherwise, it cannot go through the samples and create current of charge. Because of the existence of gap, if your Fermi level is put inside of the gap, you have to do something to excite the electrons in the valence band to the conduction band to make conduction happens. And this happens at finite temperature with a probability exponentially suppressed by the gap. So the probability is proportional to e to minus gap, which is delta, divided by T, which is the temperature. So the lower the temperature, the smaller the probability to get excited. If you go to 0 temperature, then the conductivity is exactly 0. And this is the behavior of band insulator. This is the behavior of conductivity of a band insulator. We call this coefficient in front of 1/T, the activation energy. So by this argument, we find that the thermal activation energy should be linear in delta of the same scale as the gap delta. Okay, that's for insulator. What about metal? So here I show you the case where the Fermi level is inside the conduction band. In this case, you don't need to pay finite energy to obtain empty states, because around the Fermi level, you can see like here, there are many empty states in the conduction band available for electrons to be used for conduction. The same thing happens if I put Fermi level inside the valence band. Here, instead of electrons, you have holes. For holes, it's just a dual object of electrons. You can think of it as Previously, I say that electrons are like water. Here you can think of holes like bubbles inside of the water. So if you flip upside down a bottle of water, the behavior of a bubble inside of the water just looks like a normal particle. So a bubble goes up because of the density difference between air and water. If you look it upside down, you will see that it's just like you throw up a stone in your normal life, and this stone will fall up. It will fall down. Just the same behavior. So hole is just like a particle. The only difference between hole and electron is that hole has positive charge and electron has negative charge. Mathematically, I think you can think of them as a dual object between each other. Okay, let me go to let me go to the detail of experiments. That's what physicists measure. So in experiments, they take a sample and apply current across the sample. After they apply the current, they put a voltage meter to measure the voltage. And they found the conductance as the ratio between voltage and current. This is all you know probably from high school physics. And conductance is just 1 over the resistance. As I mentioned before, the behavior of conductivity for insulator is proportional to this exponential factor. If you plot the logarithm of conductivity as a function of inverse temperature, you will get a linear curve, which has the slope equal to the activation energy. What about metal? So for metallic sample, if it's clean, there's no scattering for electrons. So when you put current drive across the sample, on one side, there will be more positive charge. On the other side, there will be more negative charge. And since negative charge attracts positive charge because they are unlike charge, electrons will go from one side to another. If there's no impurity inside of the system, there's no scattering, and you would expect a ballistic transport. So electrons just get accelerated by this electric field created by this charge. However, if you have disorder in the sample, what disorder did is they scatter electrons. So instead of ballistic transport, where electrons can go straight ahead without any scattering, now they will be scattered back and forth between electrons, between impurities. Here I show you a case of charge impurity, where impurity carries charge, and they interact with electrons via Coulomb interaction. So blue represents negative charge, red represents positive charge. So electrons get scattered back and forth. This is called diffusive transport. This scattering or this diffusion inside the sample will lead to some residual conductivity for metal. If there's no impurity, we would expect that there's no resistance at all, and conductivity should go to infinity. But because of the existence of impurity and scattering, even at lower temperature for metal, there's some still the conductivity is still some finite value instead of some divergent value. This is what we expect in physics. There's no physical quantity, no physical observable should be divergent. So the behavior for metal is very different from insulator. Conductivity doesn't decrease as you lower the temperature, it keeps a constant. This is the behavior for metal. So here comes the puzzle from experiments. Many experiments are dealing with insulator. For example, in this bilayer graphene, where they put perpendicular electric field to the graphene, they actually lift the energy degeneracy around k equal to 0. So the lowest two energy bands has a gap This is shown by this EG here in this plot. This experiment is done by Pablo's group in MIT. So they can theoretically estimate what's the size of the gap. So as I tell you before, if you know what's the size of the gap, you know the slope of the conductivity as a function of inverse temperature. But when they do the measurement, this is 1 over rho. Rho is resistivity. 1 over rho is just the conductivity. When they measure it, they found that instead of a steep slope, which is equal to the gap. By the way, theoretical estimation for the gap is several hundreds of milli-electron volts. If you convert it into temperature, it's almost 1,000 kelvins. However, when they do the measurement, they get something, they get the slope much smaller than the theoretical estimation. So it's 2 orders of magnitude smaller than what they expected. If previously they expect 1,000 kelvins, here they only observe 10 kelvins. So the slope is much smaller than they expected. Also, you can see that at high temperature, the slope is bigger. As you go to smaller temperature, the slope gets much smaller than high temperature regime. I should remind you that for metal, the behavior is almost like a constant. Is a constant. So this shows something like if it's first insulator and then it approaches something like metal. Similar experiments are done in other material like topological insulator. The interesting thing about this material is that you can observe content anomalous Hall effect in this system. In this talk, I will skip the discussion of content anomalous Hall effect, although it's interesting. The only thing we need to know about this material is that what they did in experiments is also they put Fermi level inside the gap of 2 bands. So they expect the system to be insulator. Again, when they measure the conductivity, they see much smaller slope as a function of 1 over temperature. Here you can see indeed, when temperature change more than 3 times, conductivity only change like a factor of 2 or so. So it's very small change. If you convert this slope into activation energy, it's 1 Kelvin, but theoretical estimation of the energy gap is 100 times larger, like 100 kelvins. So how to understand this phenomenon?
Excuse me, Huang. May I ask one simple question here?
Sure.
Sorry to stop you.
Doesn't matter.
I want to make sure that I understand you correctly, that this is red one is a direct conductivity and blue one is the Hall conductivity, right?
Blue one is the fluctuation of Hall conductivity. You can ignore it for now because I'm not talking about Hall conductivity.
You are just mentioning the
experiment is
red
for
one.
content. Yeah, we only talk about the red one, right?
Okay, so as I understand, then temperature is high enough, the slope is high, but for the near the 0 temperature, the slope is smaller.
Right.
So I mean, if I understand, for the high temperature, the slope, red slope, which is higher, this slope is in the order of the activation energy. But for the low temperature, this is much slower than the activation energy. Is it? Do I understand you?
Or you can think that the activation energy becomes smaller and smaller if you lower the temperature. Because activation energy is defined as locally as the slope of this curve.
But is it true that?
Or you can think of it, maybe you want to say that at lower temperature, the slope is much smaller than the gap.
So is it possible to measure the gap by using another method, a different method?
What do you mean by different method?
Yeah.
I think
Mm.
experimentally,
Mm.
if you use transport, this is one way to measure the gap. You can also measure the gap using something like STM or optical or optics.
Yes.
You can measure it.
So
I will comment about it later, or I can comment it now. So previously I say that theoretical estimation of the gap is like 100 kelvins for topological insulator. This is confirmed by optics and STM measurement, which is different from transport measurement. So, for other experiments, instead of transport, they actually get agreement between theory and experiments. So what's strange is that the transport doesn't reproduce the agreement. Transport says the activation energy is much smaller than the gap.
I see.
And yeah.
Okay, I understand.
Does that answer your question?
Yes, thank you.
Okay, thank you. Let me continue. So how do we understand such phenomenon? Like the activation energy at low temperature is 100 times smaller than what we expected. So people naturally think maybe disorder would do something, because all our understanding of previous picture of insulator is based on the fact that we ignore impurities and disorder. So if there's no disorder, electrons are pinned inside of the insulator and they cannot move. So what's the role of disorder? A natural guess for the role of disorder is that, similar to the case of metal, disorder can kick out electrons which are previously pinned inside of the insulator. Because in metal, we know that electrons are kicked out back and forth by disorder. So maybe in the insulator, the same thing happens and electrons are kicked out by disorder so that they can move inside of the insulator somehow to increase the conductivity. So this is very intuitive way and hand-wavy way to understand what's possibly happening in experiments for these transport experiments. So let me go into the detail and show you indeed this is maybe the correct physical picture to understand it. So here, let me describe the random potential and screening for inside this system. So imagine you are an electron. The most important thing you should care about is what's the potential you are experienced by those random impurities. To calculate this random potential, we care about the two most important quantity we care about is the mean value. But this is trivial in our case because we think impurities, positive impurities and negative impurities are equally distributed in space. So this mean value gives you 0. And the other important quantity you should care about is the variance of this potential. If you think impurities doesn't have any correlation with each other in position, this variance can be calculated very easily through this integral. So here you just integrate over some volume, which is R cube. Here, capital N is the 3-dimensional concentration of impurities. So capital M dr cube gives you the probability to find one impurity inside this volume element, dr cube. And you integrate over the Coulomb potential from those impurity, E squared over kappa R squared. Kappa is the dielectric constant of this material. This integral can be calculated very easily, and you can show that the variance is linear in the volume R. So this has a very
sorry. I'm sorry that could you just tell me the default definition of the notation. What is the 3D concentration? Excuse me.
3D concentration is the number of impurities per volume.
Aha, so you mean volume is R to the power 3?
Yes, actually we think of uniform concentration, so it doesn't matter which volume you take. As long as you take a volume, you can get the number of impurity inside of it using this concentration.
And sorry, so you are computing the variance of the potential uniformly distributed disorder impurity.
It's not uniformly distributed.
Yeah,
I mean, they are randomly distributed, but the probability that you find one impurities inside the volume is given by n and dr cubed. So you can think of the probability densities is a constant.
So what
does it answer your question?
I mean, I wonder why you're computing the E square over kappa times R and taking square. This is a electric energy, but coming from the origin. But impurities are scattered in the space, so each term is different. But why you
yes, I'm just saying that. Sorry.
Why you can replace just one single term from the Coulomb potential?
You can think of it in this way. So electrons are sitting in the origin, and there are many impurities sitting around of it. The distance between the electrons and those impurities is described by this R.
So,
because it's random variable, so I can. So this is the probability that I found impurity at some distance R, and the potential of it is this value.
I see. So
and then
in some sense, the disorder potential is a kind of the J-realm that they are in a kind of uniformly or person-like distributed. That's why you can have this kind of approximation.
You mean what's the exact form of distribution of impurities? I don't think it really matters as long as the correlation between position of different impurities is 0.
But anyway, so yeah, I think this computation is natural. But in some sense,
this is very natural.
it is a kind of distributed nicely that effectively energy, potential energy is coming from this term. Okay, okay, so I agree. Please go ahead.
Okay, okay. I'll continue. So the consequence of this calculation shows you that this variance of potential is linear in the volume you integrate. R is the size of the volume. So if you take larger volume, you get larger variance. So it seems like the potential fluctuation will diverge if the volume you integrate goes to infinite. But as I told you before, in physics, there's nothing divergent if it's observable physical quantity. So there must be some cutoff of the volume. In physics, we describe this cutoff in this electron system as the screening length. Sorry. The reason we have this screening length is pretty natural. So because impurities are charged and electrons is also charged. Electrons are also charged. So they will move around the positive impurities because they attract each other. And there's a cloud of electrons around those positive impurities. In this way, they can, if you go to larger distance, the potential provided by this cloud, this object consists of the cloud and this positive charge has smaller potential if you go to a larger distance because it looks like a neutral object. And we describe the potential at which we describe the distance at which point the potential effectively decays to zero. We describe this distance as the screening length lambda. So that's the physics of screening. If you take a specific model, we can actually calculate what's the screening length. For example, just take the two-dimensional small gap semiconductor. We can use this spectrum to calculate the density of states. Density of state is just how many electrons states you have in some certain energy interval. So here, screening length is inversely proportional to the density of states because the more electrons you have, the smaller screening length or the better screening you have. Because if screening length goes to zero, this means you kill the potential entirely, and screening is perfect. So in this way, you can write the equation for lambda in terms of gamma. That's one equation, and as I mentioned before, there's another equation of this gamma square, which is the variance in terms of the integral related to the cutoff of this lambda. You have two variables, two equations, you can solve for them. Here, alpha is the fine structure constant in this material, defined as E squared over kappa h bar c. Sorry, here it should be V instead of C, which is the Fermi velocity in this material. And we assume below here and below that this parameter alpha is much smaller than 1.
If I may ask, what is the variable x? So there is lambda is x divided by.
I write it. I mean kappa. This is just my handwritten kappa.
Ah, okay. And kappa was what
the dielectric constant in the material.
Ah, okay.
It's just like some renormalization of the charge.
So kappa is like epsilon divided by epsilon 0?
Yes.
Ah, okay. Now I understand.
Sorry about it. I should explain it more carefully.
No, you're doing a good job.
Okay, let's move on. So let's think about how electrons distributed in this random potential. I will show you that actually it creates electrons and hole puddles in the case where the potential fluctuation is much larger than the gap. So here I show you a plot, which is a cross section for the energy landscape along some direction, along a specific direction. You can see that the bottom of this conduction band is shown by the upper curve, and the ceiling of the valence band is shown by the lower curve. And they are bent up and down by the random potential. However, our Fermi level is fixed. It's fixed in equilibrium. So it crossed the Fermi level crossed the random potential at some point. And if there's a region above it, it's filled by holes. If there's a region below it, it's filled by electrons. So this red region are holes and blue regions are electrons. The size of this and the distance between holes and electrons is W. Actually, there's a very simple way to calculate what's W. You can simplify the shape of random potential into a triangle. So the half size of this triangle is the half bottom of this triangle is just half of the screening length, and the height of this triangle is gamma. And just by two triangles similar to each other, then the height, the ratio of the height of two triangles and the ratio of the bottom of two triangles should be equal. And in this ways, you get the ratio between W and lambda is equal to the ratio of delta of and gamma. So you can calculate W as just equal to lambda multiplied by the ratio of delta over gamma. So it's smaller than lambda by a factor of delta over gamma. I should remind you, in this case, I consider gamma much larger than delta, so that you can move the energy band up and down outside of the gap. This plot is a different view of the system looking from top to bottom. So this is the top view plot of this curve. This is the cross section of this top view curve. So actually, the shape of it is more complicated. They are fractals of many fingers. So if it's random potential, you naturally expect that if you draw some equipotential of the random potential, you should get some shape like a fractal. So here we also get some shape of fractals, although I just plotted schematically. Later I will show some plots which is numerics. The size of the fingers of this puddle is described by this quantity A. And we know from the knowledge of fractals, they always have some strange exponent. Here the exponent is 4/3. So here I show you a numerical plot taken from Ischenko's review. The dark region is below the Fermi level, and the white region above the Fermi level. This is the plot of the equipotential lines. And you can see that indeed they are structured like fingers. You can see here, and the whole shape of it is a fractal. This all reminds me actually the shape of octopus balls or takoyaki in Japan, because when you pour out some liquids in the container, if you don't do it very carefully, they always connect each other and make something like the shape of these puddles. Here I show you another plot, which is a bound model. Here you can think of this bound as one electrons connecting to each other, and it makes a shape like a fractal. You can calculate the perimeter of this fractal, and you get another strange power, which is 7/3. If you ignore the microstructure of those fingers, you can simplify the whole picture like this. So the diameter of one puddle is A, and they separate from each other by distance W. Okay, we have all ingredients to calculate the hopping conductivity, which we want to calculate because we want to compare theory and experiments and see if we can explain the experiments. So here I show you a schematic plot of the potential as a function of position, taken only one electron puddle and hole puddle. So because of the existence of gap, electrons cannot go through this gap if it's classical. So this gap is like a wall. There's no people can cross the wall without breaking the wall in classical world or in our normal world. But electrons are actually more interesting object. So quantum mechanically, it's described by these wave functions. This is the probability amplitude of, this is the probability of an electron as a function of space. So indeed, when electrons wave function cross the region of the gap, its probability amplitude decrease exponentially. Later, I will show you that this exponent inside of this exponential factor is equal to the action, which is another physical quantity we will calculate later. But as long as the wall has a finite length, you always have some finite leakage outside of the wall. So there's a small probability, there's a small chance for electron to tunnel through this gapping region. Because electrons can tunnel through the gap, so we can think of what's the charging energy Namely, you put an extra charge from outside to inside the puddle. You can, in order to calculate the charging energy, you can look at the capacitance of this puddle. And if you know the capacitance in electrodynamics, there's a simple relation between the charging energy and capacitance, which is charge squared divided by this capacitance C. And in fact, the capacitance of this fractal-like structure is proportional to its perimeter L. That's why we are interested in its perimeter in previous slides I show you. Because of the size of a fractal is very, very large compared to lambda, this makes the charging energy very small. For example, in our 2D small gap semiconductor model, we can calculate this, we can carry out the calculation and show that this charging energy is proportional to alpha squared delta over gamma to power 4/3. I should remind you that alpha is much smaller than 1 and delta over gamma is also much smaller than 1. So this charging energy is much smaller than delta. The physical meaning of charging energy is the energy you should pay if you want to put more charge, if you want to put one extra charge inside of this puddle. That's exactly the energy, activation energy, which is the energy you should pay for transport. So here we derive the charging energy much smaller than delta. This means if the transport is through this way, the activation energy should also be much smaller than delta. So it seems like we can explain the experiments in this simple way. But this is not the full story. Here I take a picture from electrical engineering community where they actually make real capacitor using this fractal structure because it saves space in finite area of chips. You can make larger capacitor by designing the capacitance in this fractal-like shape. I just think this is funny to take a look at. However, that's not the whole story. Actually, there's another mechanism that electrons can use to decrease the activation energy. We know that if we lower the temperature, the exponential factor sitting inside of the conductance decrease very fast. So is there any better way to make the decrease of these exponential factors smaller? Actually, there's indeed one way to do that. This is the variable range hopping. The idea of variable range hopping is actually very simple. So previously, I showed you an electron hop from nearest neighbor puddles. So it hops from the left side puddle to the right side puddle across one energy gap. Here, electrons, instead of hopping through nearest neighbor puddles, it hops through many puddles. So it should cross many gaps. What's the good of it? Why this is better? Because if you go to longer distance, the Coulomb energy between this puddle and another puddle which has a long distance from it is described through the Coulomb law, which is E squared over kappa R. As long as your R is large enough, larger than the perimeter, you can get the Coulomb energy smaller than the nearest neighbor charging energy we calculated before. So this decreases the exponent, decrease the factor inside of the exponent and makes the conductivity bigger. Oops. What happens? Can you see my screen now?
Yes, I can.
Okay, let me continue. But there's a price paid for it. Because you need to cross many puddles, you have to do many tunneling through the gaps many times. So there's a price you need to pay in the exponent, which is the tunneling. So R over A is the counts how many times you should cross the puddles, and S1 is the action, which is the price you need to pay for cross a single gap. So the whole expression for the conductivity is described by these two exponents. The first term is tunneling. The second term is the thermal activation through the Coulomb energy. You can actually optimize this conductivity because you can see one term grows as you increase R. The other term decrease as you increase R. So you can optimize this expression and get some optimized distance of hopping. And you will find that this is a function of temperature. That's why we call it variable range hopping, because the hopping distance changes if you change the temperature. And you plug in this optimized temperature back to the original formula, you get the conductivity, which is proportional to 1 over temperature to power 1/2 instead of to power 1 before. So this is a smaller decreasement compared to the previous linear decreasement as a function of 1 over temperature. And this is the famous Everest-Shklovsky variable range hopping. Also, if you just look at the local activation energy, namely you take derivative of this function, this is equal to the square root of T0 and T. T0 is just some constant. So this activation energy decrease if you lower the temperature, which is similarly seen in experiments. So now let me collect all the results. There are 3 mechanisms of conductivity. One is described by in high temperature regime. It's just the normal normal and activation energy equal to delta, the gap. If you go to lower temperature, you go to a regime where you have smaller activation energy equal to the nearest neighbor charging energy. And if you go to even smaller temperature, you can use variable range hopping mechanism and get to an even smaller decreasing of conductivity. Okay, and this curve looks just like experiments if you ignore the details, if you still remember experiments. So last, I will show you the, what's the time now?
Don't worry about the time.
Okay.
Don't worry about the time.
This is my final several slides. So in the end of the talk, I will talk about the insulator-metal transition in this system. So as I mentioned before, we care about the action because this describes how transparent this gap looks like for an electron inside the puddle. The larger the action, the smaller this exponential factor, and the more difficult for electron to tunnel through this insulating gap. So in this case, you will expect an insulator instead of a metal. On the other hand, if you have a very small action, this means it's very easy to tunnel through this gap. The gap is almost transparent for these quantum mechanical electrons. And in this case, you should get something like metallic behavior because essentially electrons don't feel anything about this gap. They just go through it without any troubles. So one way to distinguish insulator and metal is to calculate this action and see whether it's larger than 1 or smaller than 1. Here we see that this action is actually proportional to the distance of this gap. So the larger the distance of the gap, the bigger the action. It's linear in the distance. The reason, so here in this slide, I show you a way to understand why disorder can increase conductivity from the sense of action. So if you have smaller random potential, weaker disorder, actually you'll get bigger distance separation of puddles. This W describes the separation between puddles. If you have larger disorder potential, you get larger slope of the potential, and eventually you will get a smaller distance because if the slope is larger, you can cross smaller distance to reach the same height of the gap. So that's the reason why increasing the disorder can actually increase the transparency between two puddles. This is because it actually shrinks the distance, shrinks the separation between two puddles. If you make your disorder go to infinity, this W will shrinks to 0, and it's exactly transparent. So we can calculate this this action as in a specific model, which is the 2D small gap semiconductor. So the action is linear in the separation distance. And in physics, we know that action is equal to position multiplied by momentum. For this small gap semiconductor, the momentum is played by the role of delta over h bar v. And you can substitute the expression of W, which we calculated before, into this expression and solve for the equation S equal to 1 to get at which point S is equal to 1 and the system experience an effective insulator metal transition. And in this case, the critical strength of gamma is equal to alpha to minus 1/2 power. I should remind you that alpha is a small parameter. So this alpha to minus 1/2 is bigger than 1, much bigger than 1. This is not the full story because in physics, actually we describe the insulator metal transition not through tunneling action S, but through its conductance, dimensionless conductance. But the result is actually quite similar because tunneling action describes the same physics as insulator metal transition. So if you want to go through more careful calculation of conductance, in the end, it shows the similar results, only logarithmically different from this result shown here. So the reason we have logarithmic correction is because for conductance of a puddles, instead of just the transparency E2 minus S, this E2 minus S describes the transparency of the gap. Instead of this factor, you have another factor which is linear, which is proportional to the perimeter. This is because the larger the perimeter, the more chance for electrons to finish this hopping, because the larger the parameter, the more position for electrons to sit in the perimeter to find a place to be hop. That's why we have this factor linear in perimeter here, and because this is not an exponential factor, so it only changed the result logarithmically. Okay, let me end the talk with some comment about comparison with experiments. So as I mentioned before, in the experiments of bilayer graphene, we should expect that everything should be dominated by the variable range hopping mechanism, which is the lowest temperature mechanism, because in that case, we don't have small parameter alpha, but we have alpha is equal to 1. This is because for bilayer graphene, it has very strange, I should not say strange. It has some material property such that its dielectric constant is small and its Fermi velocity is small, so that the fine structure constant, which is inversely proportional to dielectric constant and Fermi velocity, is bigger than what we expected. So for this system, alpha is equal to 1, and the regime between the regime of nearest neighbor hopping will vanishes. So if we go to lower temperature, you instead of go through the nearest neighbor hopping regime, you go directly to the variable range regime. That's similarly seen in experiments, probably, because maybe I should remind you experiments. Yeah, this is the plot of experiments. So actually, they also fit them differently using nearest neighbor hopping and variable range hopping.
But here for the experiments, I can only see 2 regimes, no? Or maybe I'm not seeing the third. So in the
yes, 2 regimes. That's what I want to say, because nearest neighbor regime is eaten out by the big parameter. So instead of 3 mechanisms, you have 2 mechanisms. Yes. Last thing I want to comment about is the topological insulator experiments. So every analysis above can be done similarly for topological insulator thin films. The only difference is you have different expression of screening length and gamma. So you should calculate those expressions differently, but it's all similar. So our prediction for TI experiments, for topological insulator experiments, is that in their experimental temperature range, we predict that the activation energy is dominated by the nearest neighbor hopping regime, where you have a smaller activation energy, but still it's linear in 1/T. This activation energy is 20 times smaller than the gap. Although it's not exactly like experiments which shows 100 times smaller than a gap, but I think it shows the essence of this physics. Because during all the calculation I make above, I ignore all the numerical numbers. Okay, so this ends my talk, and thank you for your attention.
Thank you very much. This was indeed very pedagogical. Are there any questions?